Everybody, we continue doing electrostatics. So here is the problem 3 stars. So why 3 star? Because it's kind of harder level than it was before. And the hardness and complexity of this problem is connected with sort of kind of electrodynamics. However, still statics. Yeah, it's interesting because within the statics we still continue a charge leakage. Charge leakage is definitely electrodynamics because in this case, charge is exuding from an object. In this case, it goes off the spheres. All right, too many words. Let's have a look at the problem itself. So have a print screen or screenshot or I don't know, pause the video and of course try to do by round. And by the way, if you're new here, so consider a subscription to my channel because new videos is coming soon. Alright, so here is about spheres that initially are separated by distance r and they release off. Alright, so here is about two spheres separated by distance r hanging on threads with the length of L, which both pinned to point P. Here is the point according to the figure. And as you can see, the r distance of separation is smaller in comparison with their length of the strings. So it means they're pretty much close to each other. Okay, so first of all, how we can use this condition, of course, we can describe as a deviation of by the small angles from the vertical position. All right, so that's why I just put a vertical line down. Okay, so that's going to be a vertical line, and here's the small angle of deviation. Of course, for both spheres is going to be this angle is going to be the same, so I mark as theta angle of deviation, and they at time t equals 0 they're released. All right, so what it means that we need to find the rate dq dt of charge leakage of each sphere if the approach velocity v of the spheres is given by as v is proportional, basically inversely proportional to the square root of the distance at a given time, and b in this case is just the constant. Of course, we need to find the charge leakage from the sphere due to the fact that when they come to each other, there is with given time there is more and more value of the electric force that one sphere is basically affected by another one. Okay, so it means that we can take any given spheres when it's divided by angle theta, and let's draw up the free body diagram. So that means we can apply the forces. Okay, so what we have, of course, we have tension force from this thread. Okay, let's mark as T. We have gravity force, which can be expressed as m times g, and we do have electrostatic force of interaction at any given moment of time. And due to the fact that distance r is the variable, so it's changing according to the time, so it depends on time, so we understand that electric force is also variable due to the fact it's inversely proportional to the distance between interacting objects. However, hold on, so spheres are very close to each other, and as you remember, we discussed the problem about balls, charged balls, which are very close to each other. So that's why actually the coulomb formula ceased to work. Okay, so what it means in this case, because we do have spheres, we can neglect any charge relocation in this case, because it's sort of extended body, but we can think that as if it's all charges are actually not relocated within the surface of the sphere. Okay, let it be so, otherwise it's impossible to solve this problem if the Coulomb's law is not applicable, unless you need to know a given formula for the force, in this case for the force of electrostatic interaction. All right, so that's why we just put negative sign. So let's say we do have excess of electrons on both spheres, okay? And that means the interaction force is going to be the force of repelling. So in this case, we put Fe as electrostatic force. All right, at a given moment of time, we can put all force together and describe according to the second Newton's law. And let's write down all the equations. So we've got basically the coordinate system and the reference frame as yx in this case, and we can put on the vertical axis, let's say y-axis, we can say that it's going to be t cos theta. So in this case, it's going to be, hold on, something wrong. Okay, t cos theta is going to be equal to mg. Okay, this is vertical direction. And what about the horizontal one? So electrostatic force is balanced with the horizontal projection of t. So that means we can write t sine theta is going to be electrostatic force. And basically, to get rid of t, tension force, because obviously there is no way to know the value for that, we're not given that, so we can divide sine theta to cos theta, basically the second by the first equation, and get a tangent of theta and equate this to electrostatic force to mg. All right, so in our particular case, first of all, let's use geometry and express tangent theta. So the way we can do this is to use right angle triangle. Let's use that. So we can have L, so let's say this is right angle triangle, and to use tangent, so we need to take the opposite side, which in our case is going to be r over 2. So it's going to be r over 2, and the height in this triangle from P to this point, that's going to be the side, we can use as L cos theta. Yes, definitely L cos theta in this case. So that means this part is going to be L cos theta. L cos theta. But the problem is that we do have L cos theta again, so that's why maybe it's better, to use Pythagoras theorem. Yeah, it's better. So L squared minus r squared over 2. Okay, there's going to be the square root then, because obviously we need to have theta on one side only. So there's going to be L squared minus r squared over 4 in that case. All right, and what do we know according to the statement of this problem? R is negligibly small in comparison with L, so we can write this is about R over 2L due to the fact that R is much, much less than L, the length of the string. Okay, so that's why we've got tangent, and we can write the following. So R over 2L is going to be equal to, so what about electrostatic force of interaction between two spheres? So we can express as Q squared, or again Q. We're not given, but we're going to use. So if we put charge as Q, and over distance of separation. So as you can see, according to the graph, so the distance is between the centers. So that's why this works. Where K you can write as 1 over 4 pi epsilon 0 if you like. So if you put that instead of K, so we can have the following. Q squared over, and from there we can have 4 pi epsilon 0. So that's going to be mg distance squared, and what we need to put also, I guess that's it. All right, so that's what we have right now, and from there we can express Q, because our primary goal is to find the rate of change of the Q. So that's why what we're going to do, we're going to use Q expression. So that's why we need to write first expression for Q and only then try to take basically a derivative, because we need to find the rate of change. So Q squared, yeah, let's take Q squared from here. So Q squared is going to be equal to 5 pi epsilon 0 and G R cube and over L. So that's going to be the final expression. So what about, yeah, I think that's correct. And finally, we need to take derivative from both sides. In other words, we need to differentiate with respect of time. So here is going to be implicit differentiation because we're going to apply this operator to both sides. So if we differentiate, so according to compound rules, okay, compound function rules, so we can have the following, okay, and just maybe a little bit lift it up. Okay, so right now we take in derivative, so that's why it's going to be dq dt, but because q squared is sort of compound function, we need to put 2q in before, okay? So that's going to be 2q before, and finally we've got 2 pi epsilon 0, that's coefficient, and g over L, and if you take that, it's going to be 3 r squared and dr dt. And if you have a look at this component, dr dt is basically the velocity of the approach of two spheres, or I mean, in this case, it's basically the change, the contraction of the distance between them, right? Because r is the distance between them, and that means we can consider as the contraction of distance in this case. So that's going to be velocity of contraction. So that's why dr dt, according to how velocity of contraction is dependent on r, is just b over square root of r. So that's why that's going to be v, and instead of that we can put this into the formula, okay? So we've got the following: dq dt is going to be equal to 2 will be cancelled, and we'll be left with the following: 3 pi epsilon 0 mg over L, and that's going to be r squared, yes, and here's going to be b over square root of r, as sort of the final formula, okay? But what we're gonna do in this case, I think we need to express q, because we're not given q directly, so that's why instead of q, I guess I forgot to put a q, yes, down below, but instead of q, we can take the square root of. So that means from there, let me see, yeah. So we can take the square root according to our original formula from here. So let's say this formula 1, and that's formula 2, sort of final formula. So that's why instead of q, you can put q here and say where q is equal to square root of 2 pi epsilon 0 mg x, oh wait, yx, r cube and over L. That's going to be the final formula. If you like, you can plug Q down below and maybe recalculate all that. So I think that that's definitely possible. But I don't do that because the main sense, I think, is pretty obvious right now. So that's going to be the rate of change of charges, rate of change of charge leakage, in this case, of each sphere due to the fact they approach to each other, and due to the fact that electrostatic force of interaction between them is increasing every time while the distance is contracted. All right, there was of course limitations in terms of we were able to apply Coulomb force and Coulomb formula just as if that's not a sphere but a point charge. Okay, that's going to be a limitation. Have a look one more time. That's a complete solution. I hope you got it. All right, so thanks for watching and see you soon.